Hello, Math 2 students. We're going to be working with a lot of radical expressions in this next chapter. So what you want to do is grab the note page that I gave you in class, grab a pen or pencil, and sit down to watch this video so you can find the 4 steps for putting a radical expression into its simplest form. The first thing that you need to know before you learn how to put radical expressions into their simplest form is how do you recognize a radical expression that is not in its simplest form. The first thing is if the radicand is divisible by a perfect square. And remember, the radicand is the number that's inside the square root symbol or inside the radical symbol. So if you can divide that number by any perfect square, then that radical expression is not in its simplest form. The next one, if the radicand is a fraction, then that radical expression is not in its simplest form. And finally, if the denominator contains a radical, then that radical expression is not in simplest form. So now that you know how to identify an expression that is not in simplest form, there are 4 steps to putting a radical expression in the simplest form. The first step is to reduce. This is something that you're very familiar with. That's when you divide the numerator and the denominator by the greatest common factor. So in this problem, here in black, we have the square root of 4x to the third over 6x. So when we look at 4x to the third and we look at 6x, we can see that the greatest common factor, the biggest number that goes into the top and bottom evenly, is going to be 2. And they both have at least one x, so the greatest common factor is 2x. So when we divide 4x to the third by 2x, we get 2x squared. That's what's in the numerator. In the denominator, we take our 6x and we divide it by 2x, and that comes out to 3. So the word reduce is just reducing the fraction that is involved in the radical expression. The next step, step number 2, is to separate. And that's when you apply the division property of radicals to make one radicand into 2. And so if we start out with this black problem right here, the square root of 2/3, the division property of radicals says you can divide the 2 numbers and then take the square root, and you will get the same answer as if you take the square root of the top and the square root of the bottom and then divide them. So it's legal to separate one radicand into an expression that has 2 radicands, one on the top and one on the bottom. The third step is to simplify. Simplifying is what we've been working on in class already. It's when you divide the radicand by the largest perfect square number that you can find. Once you do that, you apply the multiplication property of radicals to make the radicand as small as possible. So in this example, we start out with the square root of 12. So I think of all the perfect square numbers and I try to find the biggest perfect square number that will go into 12 evenly. And so that is 4. So the square root of 12 is the same thing as the square root of 4 times the square root of 3. And the multiplication property of radicals says that you can multiply the numbers, then take the square root, or you can take the square root of each number separately and then multiply them, and you'll get the same answer. So once we take the square root of 4 times 3 and we make it into the square root of 4 times the square root of 3, we know that this perfect square, the square root of 4, actually has a value of 2. So we can rewrite the square root of 4 times the square root of 3 as 2 square root 3. So we started with a radicand of 12 and we ended with a radicand of 3. So we made the radicand as small as possible. The fourth step is to rationalize. Rationalizing means you multiply the numerator and the denominator by the conjugate. The conjugate is the number that will make the square root go away, or the number that will get the radical out of the problem. So in this example, we have 7 over the square root of 2. If we multiply the top and the bottom by the square root of 2, we'll get 7 root 2 in the numerator and the denominator, root 2 times root 2, will be root 4. But the reason that root 2 is the conjugate is because when we multiply root 2 times root 2, it causes the radical to disappear from the problem, at least in the denominator, and we have only a 2 on the bottom. So if we have 7 over radical 2 and we rationalize it, that will change into 7 root 2 over 2. Now for our first of two examples. You should write these examples right underneath the notes that you just took. So just keep going down the page and write these examples, and each column will have a step in some of the 4 columns going across, depending on how many of the 4 steps we need to use for this problem. So on our first problem, we have the square root of 9x to the third over 36, and I know that problem is not in its simplest form because the radicand is a fraction. So I need to start by taking care of that problem. I'm going to work my way through the problem until I'm not breaking any of those rules. So to start this problem, my radicand is 9x to the third over 36. And I can reduce the radicand just like I reduce any other fraction. So I want to find the greatest common factor, the biggest number that can go into 9x to the third and 36 evenly. And it turns out that that number is 9. So I'm going to divide the numerator by 9 and the denominator by 9. So now I have 9x to the third divided by 9 is 1x to the third. And I have 36 divided by 9, which is 4. And then I need to remember that that's not my whole problem. That's just the radicand. So after the reducing step, my problem looks like that. X to the third over 4. My next step is to take that radical expression and separate it. So instead of having the square root of x to the third over 4, I'm going to separate it into the square root of x to the third over the square root of 4. That's the separate step. Now, on to the third step, which is simplify. So in this problem, one thing that works out easily for us is that the denominator is a perfect square. The square root of 4 doesn't have a value of 4. The square root of 4 actually has a value of 2. So our denominator will be 2. When it comes to variables in the numerator, we have the square root of x to the third. And when you're dealing with variables, we want to find the biggest perfect square that can go into x to the third. But with variables, the perfect square is always x squared. So I'm going to separate my x to the third into x squared times x. Now I'm going to split those into x squared times x using the multiplication property of radicals. And then I still have my 2 on the bottom. So the great thing about the square root of x squared is a perfect square. So after I take the square root of x squared, I'll have x root x over 2. Now if I go back up to the very top and I look at what makes a radical expression not in its simplest form, if the radicand is divisible by a perfect square, well, our radicand is x, and x is not divisible by a perfect square. And if the radicand is a fraction, well, our radicand is an x, and x is not a fraction. And if the denominator contains a radical, well, our denominator contains a 2. So those 3 rules, we're not breaking any of them. So that can only mean one thing, that our radical expression is now in the simplest form. All right, in our next example, we have the square root of 147 x to the third y to the second. And when I look at this thing to see if it is in simplest form or not, there are no fractions. I don't have to worry about the denominator containing a radical. I don't have to worry about the radicand being a fraction. The only reason that we might have to simplify this problem is if there is a perfect square that goes into 147 evenly. All right, so I need to figure out if any perfect square number can go into 147.
I don't have to worry about 225 because it's too big. 196 is too big. 169 is too big. 144 is not too big, but it's not going to go into 147 once evenly, and it's definitely not going to go into 147 twice evenly. And then if I divide 147 by 121, it won't work. If I divide it by 100, it won't work. If I divide it by 81, it won't work. And when I say it won't work, I mean it won't come out to a whole number. All of these division problems come out to fractions or decimals. So now 147 divided by 64, decimal or fraction. 147 divided by 49, it goes in there 3 times evenly. So this is the biggest perfect square number that can go into 147. So I'm going to take my problem right now and reduce it. I'm not going to worry. But I separate it. I'm not going to worry. Simplify it. That's the step that we're on. So I'm skipping reducing because I don't have a fraction. I'm skipping separating because I don't have a fraction. Now I'm on to simplifying, and so my problem will look like this. The square root of 49 times 3 times x squared, which is, remember, that's the perfect square that can go into x to the third, times x times y squared. So now I'm going to use the multiplication property to split that up. So I have the square root of 49 times the square root of 3 times the square root of x squared times the square root of x times the square root of y squared. Now, some of these radicands are perfect squares and some of them are not. All of the radicands that are perfect squares, I'm going to make them not radicands anymore. I'm going to take out their actual value. So the square root of 49 has an actual value of 7. The square root of x squared has an actual value of x. And the square root of y squared has an actual value of y. So the front of my problem, in front of the radical symbol, I'm going to have 7xy. Now, what about the other terms here? I have a root 3 and I have a root x. Those radicands are not perfect squares, and no perfect square number can go into them. So what happens in the answer is they just remain under the radical sign. So now if we go back to the top, there's no perfect square that goes into 3, so we don't have to worry about rule number 1. And it's not a fraction, so we don't have to worry about rule number 2 or rule number 3. So now we know that 7xy root 3x is a radical expression in the simplest form.